Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be kind of taking a little deviation from what we've been talking about previously, as we're really going to try and dive into the core of an atom and figuring out how it works. Unfortunately, to do so, we have to take kind of a nice little detour to talk about light. And one of the reasons why is, as we've seen previously, molecules are really tied together by electronic interactions. So we've got things like lone pair electrons just floating around. And more importantly, chemical bonds are more or less just electrons tying together two atoms, because the atoms like the electrons and the electrons like the atoms, even if the atoms don't like each other. And this is all electronic properties. So in order to understand the behavior of our molecules, what bonds want to form, which bonds don't, we really have to understand the location and movement of these electrons. However, electrons are a little tricky to see, and our go-to method of trying to figure out where electrons are is using what are called spectroscopic techniques, which you can break up into two words: spectra, which is light, light, and scopic, which is measurement. So it's more or less a measurement of things using light. So we need to understand what light is and what it does so that we can actually talk about our electrons. And one of the reasons, and so that's really going to be the key role of light, is it helps us tell where the electrons are. And because it tells us about the electrons, it can tell us some information about atomic positions. And we can use this to figure out things like atomic trends, molecular behavior, and then eventually we can talk about a whole world of systems. Now, why can light interact with electrons? Well, it turns out light is caused by a photon moving forward in space, which essentially changes electric fields. So it interacts with anything electric. So if you have, say, a particle like an electron, say, sitting on a sea, think of it like a bobber on the ocean. Photons and light is more or less like the waves passing through. The electron can move up and down as essentially it interacts with the light. And so what we're doing is we're looking at how the electrons move based on their interactions with light. And that's really going to be the big thing with light, is because of this electric change. Because it causes oscillation in electric fields, it can interact with anything with a charge, most notably electrons. And so this is where we get into the big messy physics, which you don't have to worry about too much. But the reason why we call it electromagnetic fields is because it has an electric component and a magnetic component, which essentially is a simple way of talking about how a charged particle can interact with both electric fields and with magnetic ones. And this is going to be very important, as we're going to predominantly use photons to look at the electric component right now, but eventually we'll also use some of these magnetic components to talk about some really cool special features of atoms. So this brings us to the question of, how can I describe and measure these waves? Well, we're going to do this by taking a look at a single wave. So as the photon travels up, it's going to have essentially an increased electronic charge, and then it's going to decrease and then eventually flip directions. And that's really what we're talking about with these magnitudes of the waves. So essentially, it's going to go through one full cycle to get back to where it started, and then it will go up and down again. And this repeating distance is called a wavelength. So this is going to be the length of one full wave. It is most commonly measured in meters, or especially when we're talking about the light that we see. We're typically going to be using nanometers, because that's about the wavelength of visible light, is on the order of nanometers. However, one of the important things to remember is that this wave is actually moving forward. So I've got a particle moving forward in time. So we can also measure this in frequency. So this would be, let's say we position a measuring device right here. And then as the wave goes through, it'll go down and then up and then back to where it started. So the time it takes for for it to go through one full cycle is called the frequency. And this has units of hertz. Hertz is not just a bad pun, it is also a measurement of per second. So how many waves that hit in a single second or per second is another way of talking about hertz. And we'll use that units of measurement as well. Now, it turns out that for all waves, we can relate this wavelength and this frequency with a set equation. So the wavelength times the frequency should equal the speed, which makes sense because with the frequency, we're seeing how long the wave takes to essentially from the back end to get to the front end. So that should more or less be the speed. And it turns out that when we're dealing with light, all photons travel at the exact same speed. And that's going to be about 3 times 10 to the 8th meters per second. So light is literally as fast as it gets. Can't get any further faster than that. As soon as you start trying to, Einstein rears its ugly head and you have relativity, which is a completely different topic. But what we can use is the fact that anytime we're trying to relate wavelength with frequency, their product always has to be this same number, the same speed of light. And what this means is that as the wavelength of light tends to get smaller, it means the frequency gets faster. And this also should make a certain amount of sense because as the wavelength essentially becomes lower and lower and lower, the wave has to the photon doesn't have to travel as far to have a repeating pattern, which means it will start passing your measuring device at a much quicker rate. You're going to see more cycles. And this ends up resulting in a classic inverse relationship. Wavelength can be given as the speed of light over frequency, and similarly, frequency can be given as the speed of light over wavelength. And there's a lot of ways we can relate this to real world problems. So one of the cool parts about this is that the longer a wavelength of light, what we tend to find is that the more objects that light can pass through. So essentially, light can be stopped by any object bigger than its wavelength. So if I have a wavelength of 1 centimeter, an object of 2 centimeters can go ahead and block it. Also, because it vibrates less, the longer the wavelength, the less energy it takes to produce. Now, one of the important things is that light doesn't just apply to visible light. It applies to anything on the electromagnetic spectrum. So this also includes good old-fashioned FM radio. So it turns out that those call signs you know from radio actually have a real purpose. So for example, the local campus radio is 88.7. Well, what that actually means is that the radio signal is produced at 88.7 megahertz. So what kind of wavelength is that? So in order to do this, we can use our equation, plug in our speed of light and megahertz. Well, what the heck is a megahertz? So it's a mega, so this is 10 to the 6 hertz, which is the same as per second. So we can go ahead and do our conversion of megahertz to 88.7 times 10 to the 6 impacts per second, relate that to the speed of light, plug it in, and it turns out that we have a wavelength of about 3.38 meters. Now, this actually has a real physical consequence because in order to generate electromagnetic radiation of this wavelength, I need to have an electric charge that essentially can vibrate along a mass that is some integer of half that wavelength. So in order for the radio station to essentially transmit, I'm going to want a transmitter that's an integer of half this wavelength. So in other words, to transmit our signal, we need a metal wire that's at least 1.7 meters long, preferably a little longer to get a clearer signal. But this is kind of the basics of radio. And we can apply this to a huge range of the of electromagnetic spectrum. So this goes anywhere from radio, which tends to be very long wavelengths, to microwave. And yes, I'm talking about the microwave you use to cook your food. It tends to have a radiation frequency of about 2,500 megahertz, which means it has a wavelength of about 18 centimeters. So if you've ever wondered why you occasionally have a cold area, a cold spot in the middle of your food, that's because about every 9 centimeters, there will be a node in that radiation, which means that we're not really exciting the water molecules that cause our food to heat up, because that's all we're doing is using electromagnetic spectrum, electromagnetic fields to excite water molecules. And if I've got a wavelength of 18 centimeters, it means I'm going to have a node every half of that, or 9 centimeters. This is also the reason why it's very important to have a spinning plate to make sure the food rotates through those cold spots. Then we've got infrared spectroscopy. So this is a technique that we'll learn about a little bit this year, but much more if you make it on to organic. But this is also the region that's responsible for things like infrared goggles, because it turns out everybody emits electromagnetic spectrum, and people, just due to their body warmth, will release infrared light. Then we have our classic visible light spectra, which we'll mostly be talking about. UV radiation, this causes cancer because it turns out that the UV radiation from the sun can go ahead and penetrate a little bit into your skin and cause excitations in your DNA molecules, causing genetic mutations and cancer. And if you think UV can do that, turns out X-rays and gamma rays are even better. So this all just tells us about the frequency and wavelength of the light, but it tells us nothing about brightness. And it turns out brightness of the light is determined by the amplitude of the electromagnetic radiation. So a good way to think about this is that the amplitude is another way of talking about how many photons you're being hit by. And this amplitude can largely be controlled by blending together different sources of light. So if I have two sources of light that are exactly in phase, what ends up happening is that these photons get along really well together, and we get a larger amplitude, and the light becomes much brighter. If they are exactly opposing, so somebody's at a peak once the other one's at a trough, what ends up happening is that these two photons get in an argument and cancel out, and we have no light whatsoever. Now, this is kind of good to know with the fact that light has this classic wave property of interference patterns, which we'll make use of occasionally when talking about quantum phenomena. But practically speaking, there's actually a really good use of this in-phase building of amplitude, and that's lasers. Because what more or less happens in lasers is you have an energy source that produces these high energy photons, which move back and forth in a highly reflective container. And one side of the container will slowly release little bits of light, which little bits of photon, which will come out as light. And that's really what the laser is, because what I've done is I build up such a high density of these photons with the exact same frequency that their amplitudes keep building and building and building and building and building till it's really bright. And that's how a laser can be a really bright object with a single wavelength. And that's really where the power of lasers come in. So we're going to be talking a little bit more about light, but trying to relate it a little bit more to molecular phenomena, as next time we go ahead and bring up the introduction of quantum mechanics and, well, how we discovered quantum mechanics. Until then, take care.